Now, in the second half of the course, we will be focusing on machine learning frameworks. Until now, we had covered the basics of machine learning and we primarily looked at supervised learning and unsupervised learning and most of the concepts associated with them. But going forward, we will be talking about frameworks like TensorFlow, PyTorch, Keras, etc. And we will also be seeing this with respect to the neural networks. So basically, we are now entering the territory of deep learning. So let's begin. I'll define the key high level terms that relate to deep learning, including machine learning, reinforcement learning, artificial intelligence, and of course, deep learning itself. Artificial intelligence is the busiest, vaguest, and broadest of the terms that we'll cover. Taking a stab at a technical definition regardless, a decent one is that AI involves a machine processing information from its surrounding environment and then factoring that information into decisions towards achieving some desired outcome. Perhaps, given this, some consider the goal of AI to be the achievement of general intelligence. Intelligence, as it is generally referred to with respect to broad reasoning and problem solving capabilities. In practice, and particularly in the popular press, AI is used to describe any cutting edge machine capability. Presently, these capabilities include things like voice recognition, describing what's happening in a video, answering questions automatically, driving a car, industrial robots that mimic humans in a factory, and even dominating humans at intuition heavy games like the board game Go. Once an AI capability becomes commonplace, the AI moniker is typically dropped by the popular press for that particular capability, such that the goalposts on the definition of AI are always moving. We can split the concept of AI into three clear categories: narrow, general, and super. Artificial narrow intelligence (ANI) is machine expertise at a specific task. I went through a bunch of those a second ago. So many diverse examples of ANI exist today, including the visual recognition of objects, real time machine translation between a bunch of languages, automated financial trading systems, computer opponents in video games, and self driving cars. Artificial general intelligence would involve a single algorithm that could perform well at all of the tasks that I just described. So it would be able to recognize your face, translate something you say into another language, optimize your investment portfolio, beat you at chess, and drive you safely to your holiday destination. Indeed, such an algorithm would be approximately indistinguishable from intellectual capabilities of an individual human. There are countless hurdles to overcome in order for AGI to be realized. It's challenging to approximate when it will be achieved, if it will be achieved at all. That said, AI experts are happy to wave a finger in the air and speculate on timing anyway. In a study conducted by the philosopher Vincent Mueller and the influential futurist Nick Bostrom, the median estimate across hundreds of professional AI researchers is that AGI will be attained in roughly the year 2040. Artificial superintelligence is difficult to describe because it's properly mind boggling. ASI, or artificial superintelligence, would be an algorithm that is way more advanced than the intellectual capabilities of a human. If AGI is possible, then ASI may be as well. Of course, there are even more hurdles on the road to ASI than AGI, the bulk of which we can't foresee today. Citing the Mueller and Bostrom survey again though, AI experts' median estimate for the arrival of ASI is 2060, a rather hypothetical date that falls within the lifespan of many Earthlings alive today. Others argue that it could be the case that as soon as AGI is achieved, the AGI itself could conjure up ASI instantly. Perhaps to the peril or to the great benefit of humankind, deep learning models may end up contributing to the development of AGI and ASI, but it's too soon to tell. Now, machine learning is a subset of AI alongside other facets of AI like robotics. Machine learning is a field of computer science concerned with setting up software in a way that the software can recognize patterns in the data without a programmer needing to explicitly dictate how the software should carry out all the aspects of that recognition. That said, the programmer would typically have some insight or some hypothesis about how the problem might be solved, and will thereby provide a rough model framework and relevant data such that the learning software is well prepared and well equipped to solve the problem. Machine learning traditionally involves cleverly, although manually and therefore laboriously processing raw inputs to extract features from data that jibe well with data modeling algorithms. So, specific examples of machine learning models include things like linear regression, logistic regression, clustering algorithms, support vector machines, and random forests. And we have seen these before. As depicted in the figure that I am showing right now, a machine learning practitioner applying one of these what I call traditional machine learning techniques is likely to spend the vast majority of their time writing functions to manually engineer out of their data. For example, to detect parts of people's faces from pixels in a machine vision algorithm, or to detect verbs and subject of a sentence from the words in a natural language model, the machine learning practitioner would need to be an expert in language or in what faces look like and come up with clever features to extract those features from the raw data. A deep learning practitioner, meanwhile, might spend little to none of their time engineering features from the raw data. Instead, a deep learning practitioner spends their time building models that can extract these features automatically. More on that shortly. Now, another term that we have here is representation learning. Representation learning is the name of the branch of machine learning in which models are constructed in a way that, provided they are fed enough data, they learn features, also known as representations, automatically. In recent years, we are discovering that these learned features may wind up being more nuanced as well as more comprehensive than their manually curated cousins associated with the traditional machine learning approach. The trade-off is that learned features might not be as well understood nor as straightforward to explain, although academic and industrial researchers alike are increasingly tackling these hitches. Artificial neural networks, or ANNs, dominate the field of representation learning today. Let's dive into the biology to understand the historical basis of ANNs. Commonly called brain cells, billions of interconnected neurons make up our nervous system, and they enable you to sense, to think, and to take action. By straining and examining thin slices of brain tissue, the Spanish physician Santiago Cajal was the first to identify biological neurons. And in the early half of the 20th century, researchers began to shed light on how these biological cells work. Here's a figure of a hand-drawn diagram from Cajal's 1894 publication showing the growth of a neuron. So the lowercase a through e are illustrations of a neuron growing. And then there's also some neurons here from a frog, from a lizard, from a rat, and here D, that's from a human sample. By the 1950s, scientists inspired by their understanding of the brain were experimenting with computer-based artificial neurons, linking these together to form artificial neural networks that loosely mimic the operation of the natural brain cells. Artificial neurons are simple algorithms inspired by biological brain cells, especially in the sense that individual neurons, whether they are biological or artificial, receive input from many other neurons, perform some computation, and then produce a single output. An artificial neural network then is a collection of artificial neurons arranged so that they send and receive information between each other. Data, for example, images of people's faces are fed into one end of an artificial neural network, which processes this data in some way with the goal of producing some desired result at the other end. So, for example, an accurate guess as to whose face is in the image that's fed in. Of all the terms we are going to cover here, Deep learning is the easiest to define because it's so precise. Deep learning is an artificial neural network that has more than a few layers of artificial neurons. So again, going back to that same analogy, you feed an image in, you process that image through several layers of artificial neurons, and then it guesses at the end whose face was put in at the beginning. So as shown in this figure, deep learning networks have a total of 5 or more layers of artificial neurons. So they have a single input layer that's reserved for data being fed into the network. So this could be the pixels of an image. Then we have 3 or more hidden layers that learn representation from the input data. A general purpose and frequently used type of hidden layer is the dense type, in which all of the neurons in a given layer can receive information from each of the neurons in the previous layer. In addition to the versatile hidden layer type, there are plenty of specialized types of artificial neurons for particular use cases. We'll touch on the most popular ones here. So you have our input layer, we have 3 or more hidden layers, and then finally we have an output layer. We have a single output layer in deep learning network that's reserved for the values, the predictions that the whole network yields. So input layer takes in pixels of an image. Those pixels get processed through several hidden layers of artificial neurons, and then the output layer gives some prediction of who was in the picture that was fed into the network. With each successive layer in the network being able to represent increasingly abstract recombinations of the previous layer, deep learning models with a fewer than a dozen layers are often sufficient for learning the representations that are of value for a given problem being solved with a given dataset. That said, deep learning neural networks with hundreds or even upwards of 1,000 layers have, on occasional circumstances, been demonstrated to provide value. As rapidly improving accuracy benchmarks and countless competition wins have demonstrated in recent years, the deep learning approach to modeling excels at a broad range of machine learning tasks. Indeed, with deep learning driving so much of the contemporary progress in AI capabilities, the words deep learning and artificial intelligence are used essentially interchangeably by the popular press today. Alright, let's move inside the deep learning ring of this figure to explore the major classes of tasks that deep learning algorithms are leveraged for today: machine vision, natural language processing, and reinforcement learning. Prominent examples of applications that involve machine vision algorithms include self-driving cars, face tagging suggestions, and phone unlocking via face recognition on your smartphone. More broadly, machine vision is relevant to any AI that is going to need to recognize objects by their appearance at a distance or to navigate a real-world environment. Convolutional neural networks, also known as CNNs for short, are a prominent type of deep learning architecture in contemporary machine vision applications. Prominent examples of applications that involve machine vision algorithms include self-driving cars, face tagging suggestions in social media, and phone unlocking via face recognition. More broadly, machine vision is relevant to any AI that is going to need to recognize objects by their appearance or to navigate a real-world environment. Convolutional neural networks, or CNNs for short, are a prominent type of deep learning architecture in contemporary machine vision applications. A special type of machine vision model that uses convolutional neural networks is the Generative Adversarial Network, or GAN. These are beyond the scope of our course, at least in detail of what we are going to talk about today, but briefly, these GANs are capable of producing stunningly realistic novel art, such as supposedly high-resolution photographs of actually fake celebrities or paintings in the style of some great master of your choice, say Pablo Picasso. Outside of machine vision, in the sphere of natural language processing, deep learning doesn't dominate natural language applications as comprehensively as it does machine vision applications. So our Venn diagram here shows that NLP in both deep learning region as well as in the broader machine learning territory. Deep learning approaches to NLP are, however, beginning to overtake traditional machine learning approaches in the field with respect to both efficiency and accuracy. Indeed, in particular NLP areas like voice recognition, for example, on Amazon's Alexa or Google's Assistant, machine translation, including real time voice translation over the phone, as well as aspects of internet searches like predicting the characters or words that will be typed next, deep learning already predominates those applications. More generally, deep learning for NLP is relevant to any AI that interacts via natural language, be it spoken or typed, including to answer a complex series of questions automatically. A type of hidden layer that is incorporated into many deep learning architectures in the NLP sphere is called long short term memory cell, which is a member of the recurrent neural network family. RNNs or recurrent neural networks are applicable to any data that occur in a sequence, such as financial time series data, inventory levels, traffic, and weather. Like generative adversarial networks or GANs, natural language applications, RNNs, and LSTMs are beyond of the scope of what we can cover right now. The one remaining section of our Venn diagram involves reinforcement learning. To introduce reinforcement learning, I'll contrast it with supervised and unsupervised learning problems. In supervised learning problems, we have both an x variable, some input, and a y variable, where x represents the data that we are providing as input to our model, and y represents some outcome that we are trying to predict with our model. This y variable can also be called as a label. The goal with supervised learning is to have our model learn some function that uses input x to approximate our output y. Supervised learning typically involves either of two types: classification, where our y values consist of labels that assign each instance of x into a particular category. In other words, the outcome is a so-called categorical variable. Examples include identifying handwritten digits. So, you put in some pixels that represent some handwriting in one end and then have the model at the other end predict that it's a number 5 or that's a number 7. Another example of classification problem is predicting whether someone has loved a film that they've watched or absolutely hated it. So you feed in some text of a movie review in your input, and then in your output the model predicts that the person loved the movie or the person hated the movie. So in addition to classification with supervised learning problems, there are also regression problems, where instead of predicting a category, we are just predicting some continuous variable with continuous number. So examples of this include predicting the number of sales of a product or predicting the future prices of an asset like a home or a share in a company listed on a stock exchange. Unsupervised learning problems are distinguishable from supervised machine learning. Unsupervised learning problems are distinguishable from supervised learning problems in that they don't have some label y that you are predicting. So in unsupervised learning problems, we have some data x, some input that we put into our model, but there is no outcome to predict. Rather, our goal with unsupervised learning is to have our model discover some hidden underlying structure within our data. An often used example of an unsupervised learning problem is grouping news articles by their theme. Instead of providing a predefined list of categories that the news articles belong to, such as politics, sports, finance, and so on, we configure the model to group those news articles with similar topics for us automatically. Some other examples of unsupervised learning include creating something called as a word vector space to represent the meanings of words across a body of natural language data, and another example is producing novel images with a generative adversarial network like we've talked about earlier. Returning to our Venn diagram, we are now well positioned to cover reinforcement learning problems, having talked about the supervised and unsupervised varieties now. So reinforcement learning problems are completely different. They are ones that we can frame as having something called an agent take a sequence of actions in some environment. The agent could be either a human or the agent could be an algorithm, and so this agent, whether it's a human or an algorithm, it could be playing in a target video game or it could be driving a car. So perhaps the primary way in which reinforcement learning problems divert from supervised or unsupervised ones is that the actions taken by the agent, whether they are playing a video game or driving a car, that agent's actions influence the information that the environment provides back to the agent. So, the agent's constantly receiving feedbacks on the actions that it takes. In supervised or unsupervised problems, in contrast, the model never impacts the underlying data, it simply consumes it. Students of deep learning, for some reason, often have an innate desire to divide the supervised, unsupervised, and reinforcement learning paradigms into the traditional machine learning versus deep learning approach buckets. More specifically, for some reason, they seem to want to associate supervised learning with traditional machine learning and associate unsupervised or reinforcement learning or both with deep learning. To be clear, there is no such association to be made. Both traditional machine learning approaches and deep learning techniques can be applied to all three kinds of problems: supervised, unsupervised, and reinforcement learning problems. So, at last, we reach the deep reinforcement learning section at the very center of our Venn diagram here. When does a reinforcement learning algorithm earn its deep prefix? Well, it earns its deep prefix when an artificial neural network, including a deep learning network, is involved in it. The marriage of deep learning and reinforcement learning has proved to be a prosperous one in recent years. This is because deep neural networks excel at processing complex sensory input provided by real environments or advanced simulated environments in order to distill signals from a cacophony of incoming data. This is analogous to the functionality of biological neurons in our brain, in our visual or auditory cortex, which receive input from the ears and eyes respectively. So, these deep learning algorithms handling all these data, while the reinforcement learning algorithm in a deep reinforcement learning algorithm shines at selecting an appropriate action to take from the vast scope of possibilities. Together, the deep learning identifying signal from all the noisy inputs and reinforcement learning figuring out what decisions to take based on those signals are a powerful problem solving combination. Increasingly complex problems in deep reinforcement learning tend to require large datasets for these deep reinforcement learning algorithms to wade through all the vast noise as well as the vast randomness of what actions impact what outcomes in a given circumstance. Because many reinforcement learning problems take place in a simulated environment, the most popular one is called OpenAI Gym. But there's a lot of these video game style environments. Because of this, it's obtaining a sufficient amount of data and it is not a problem anymore. The agent can just play the video game for longer and so it can be trained on further rounds of simulations. Although the theoretical foundations of deep reinforcement learning have been around for decades, both deep learning and deep reinforcement learning have in the past few years benefited from a confluence of these three tailwinds. The first is exponentially larger datasets and much richer simulated video game environments. The second is parallel computing across many GPUs or graphics processing units to model efficiently with large datasets as well as the breadth of possible actions that can be taken in these complex environments. The third advance is a research ecosystem that bridges university academics and practitioners in industry who are producing a quickly developing body of new ideas on deep neural networks in general as well as on the deep reinforcement learning in particular. There you have it. So that's a tour of all the key terms related to deep learning. We've talked about artificial intelligence, machine learning, representation learning, and we've also covered specific examples of deep learning applied to machine vision problems, to natural language processing, and to reinforcement learning problems. So now I am going to show you a quick demo about how machine learning and deep learning works. Now we have seen the relationship between AI, ML and deep learning, and within deep learning there are neural networks. So machine learning is, according to Wikipedia, a mechanism by which you can teach a system without explicitly programming, and deep learning is a subset of machine learning. According to Wikipedia, the definition of deep learning is that it's a part of machine learning and it is based on learning data representations, which is nothing but you have some known data which you can use to train your system without explicitly programming it. Now this is a little difficult concept for people who are new to machine learning and deep learning, and any number of slides will almost be impossible to explain this concept. So I've decided to show you a small demo by what is meant by this. So what do you mean by teaching a system without explicitly programming or writing a code? So in this little demo, which is basically based on Google's AI experiment website, this is a public website and you can also try it. So I'm going to show you how I can train my system to recognize some objects. And for this, I will have to go to the website Google AI experiment. So let me take it to the website, and this is the Google AI experiment site, and I started to experiment already. What we will do here is that I will teach my system to recognize three objects. One is this little moisturizer bottle, then I have a foam, and then I have a bottle of water. I will teach my system to recognize these objects. I will train it first by showing these objects, and subsequently, whenever it sees this object, it will recognize it. And how do we know that it has recognized? Each time it sees a particular object, it will play this GIF. So, first object, it will play this GIF. If it sees the second object, it will play this GIF. And if it sees the third object, it will play it. Alright. So, I hope you're ready. So, let's get started. First, let me train my system to recognize this moisturizer bottle. So, I will hold it like this and I will press this train button, and I will hold it for a few minutes till it takes probably about 50 samples. And notice that I am not holding this static because it is a video recognition and not just an image recognition. So, it will take about 40 to 50 samples to get trained, and as you can see, it is 100% confident that it got trained. So this first object, it has got trained to recognize it. Now let's do the same with my second object, which is my cell phone. Now I will use the second button, do the same, hold it for a while so that it takes about 40 to 50 samples, and here we go, it got trained. So it says 100%, very good. And the last object is my water bottle. So let me hold it here, and now we use this third button to train the system to recognize the water bottle. And then you just hold it for a little while so that it can take 30 to 40 samples. Now let's see whether it has got trained. Yes, when it says 100%, alright, so we know that it has got trained, and let's see whether it's able to recognize or not. So let me show my second object, and okay, here there seems to be a little confusion, but let's see the first object and then my water bottle, and then again my second object. Alright, this time it seems to be recognizing it well, and then first object, and once more the third object. So in this experiment, I have shown you that without even writing a single piece of code, I was able to train my system to recognize three objects. Now how does this work? As shown in the previous slide, behind the scenes there is something known as neural networks, and neural networks is nothing but simulation of the human brain. And human brain has billions of neurons, and we tried to create artificial neurons that simulate the functioning of these biological neurons. Now, how does this neural network work? Again, there is a website which kind of again created by Google visually represents the working of a neural network. So let me show you a quick demo of that as well. So the name of this website is Playground or TensorFlow.org. So in this website, we can go and configure a neural network. Each of these square blocks are a representation of a neuron, and then there are several layers of neurons, and you can increase or decrease the layers by clicking on this plus and minus sign, and each layer can have multiple neurons. Again, you can configure that by clicking on the plus or this minus sign, which will increase or decrease the number of neurons. So by doing this, you can create your own neural network of multiple neurons and multiple layers to solve a particular problem. Now let's assume here that we have data from two classes, which is represented in the form of this yellow color and a blue color. So this is all the data it is looking at, and I want to use neural networks to classify this data. So we are basically trying to create a classifier, and I am using neural networks to solve this problem. So how do I do that? I start with, let's say, this particular configuration, and I have 1, 2, 3 hidden layers, and this is the output layer. So this is a deep neural network, and my first hidden layer has 4 neurons. The second hidden layer has 2 neurons, so let me increase it to 3, and then my output layer has 1 neuron. Now I will try to train this model, and how do we know that it's training or whether it's working or not? On the right hand side, it displays the test loss, which is like a measure of the error. So the moment we get the test loss close to 0, that means that the model has got trained. And when I click on this button, it starts training, and this is the number of epochs, which is basically like multiple iterations. So it takes this data and iterates to train itself to come up with the classifier. So let's quickly see how it works. So you can see here that the error is slowly reducing and almost it has become 0. So very often in machine learning and deep learning, you may never achieve a 0 error, but as close as possible to 0. So in this case, it is pretty much a 100% accurate model that you got. It has classified the data almost perfectly, the blue color and the yellow color. Now, if you're not satisfied with this because it has taken 150 epochs, you want to get it done much faster, you can probably play around with the number of layers, increase the number of hidden layers, and decrease or increase the number of neurons in each layer, and then try to do it once again. Let's see if it is faster in this case. Probably not so much. Probably not much. So it has finally achieved a kind of 0 error, but it has taken a little longer. So it is not necessary that if you increase the number of layers, the accuracy or the efficiency will increase. So you just play around and then come up with the right configuration that is perfect to solve for your particular problem. So it looks like this is the best configuration. You almost got 0% test loss. So I hope this gives you an idea about how neural networks work, and a day in the life of a machine learning engineer is all about coming up with this right configuration of the neural network, and with the right number of layers, with the right number of neurons per layer, and this is what we do in our day-to-day life. So I was hoping that this was helpful in understanding what is deep learning and how to train your systems without writing a piece of code, and how neural networks work. We have discussed many different machine learning algorithms and methods. Now, in general, you don't have to go and code everything up yourself in Python and R and Octave and other basic types of programming languages that just have machine learning capabilities. In most cases, we want to use one of the open source toolkits that has all the libraries built in. We would like libraries that have regression capabilities, can do deep learning and neural networks, that have all the classification tools we've talked about as part of them, that can do random forests, clustering, Bayesian inference, PCA. We want to be able to use those basic frameworks and then just apply it to our machine learning problem. When we have a project that involves AI machine learning, we could spend a lot of time developing the algorithm, but instead we just want to get that data, push it into the algorithm, sort of tweak the algorithm, and see the results. And the way we get there is by using a lot of these open source tools where these libraries have already been constructed for us. So let's take a look at some of the common open source frameworks that are used in machine learning. For example, Google has developed TensorFlow, Facebook has developed PyTorch, Microsoft has developed CNTK, Apache has developed MXNet, and then there's Caffe 2, and there are many more. Now the question is, if you are going to start down the road of a machine learning and AI project, which one of these should you choose? They are all a bit different and they have strengths and weaknesses. Some of them are easier to use, some of them are more difficult. Some of them are very specialized on specific types of machine learning. So, which one is the best for your project? What we are going to do is survey just a couple of them. We are going to look at 4 of the popular frameworks and look at their pros and cons and their capabilities. So let's start. TensorFlow is one of the most popular machine learning frameworks in existence. It was developed by Google Brain back in 2015, and since then it has become very popular and it's extensively used around the world for all kinds of machine learning projects. Some very famous customers of TensorFlow include companies like Uber, Airbnb, Dropbox, and others. And if you use Google Translate, that is using TensorFlow on the backend to develop machine learning applications that understand how to translate one language into the next. Now, some of the pros of TensorFlow is that it's really good around documentation and its guidelines because it has such an extensive community of developers. So if you are doing something in TensorFlow and you want to get help, you want to reach out to the community, you are going to find a lot of people that are very experienced in TensorFlow and are going to be able to help you, and there's going to be code available on GitHub and other places. So there's a big community of support if you are using TensorFlow. Now, one of the things that it does require is knowledge of Python, and you do have to have some experience with NumPy arrays and how to program them. That means that there is a little bit of barrier to entry using TensorFlow, but it's not that high. A lot of people have used it and there's a lot of great documentation to learn these different aspects. Now, one of the key advantages of TensorFlow is the ability to visualize it in real time, and this is called TensorBoard. When you're deploying a machine learning mechanism, interpretation of the results can be one of the most challenging things that you will have to deal with. Both, am I getting the right data set? So, am I looking at the right data? How is my training set doing? And am I tweaking the variables and the features correctly? Well, with TensorFlow, it makes it very easy to visualize and understand, debug, and then optimize my different features in the TensorFlow program. You can use TensorFlow to visualize your TensorFlow graph, and you can get qualitative metrics about the execution of your graph, and you can even see how it's functioning as images are being passed through a deep neural network. TensorBoard can also give you not just a pictorial representation of the neural network, but it can also show you the accuracy of how well your training sets are doing and if you need to improve them. So here is an example of one model visualization in TensorBoard. And because of TensorBoard, we can say that TensorFlow really does excel in this area and it has become an ideal choice for a lot of machine learning projects. Now, another popular framework is PyTorch. Now, this was developed by Facebook's AI research group. This is commonly used by Twitter, SFDC, and other big companies. Similar to TensorFlow, it includes capabilities for regression, for deep learning, for classification, and many of those very common and useful algorithms that we've talked about. So, one of the key advantages of PyTorch is that it's known to have a very simple architecture, making it a very easy entry point for the new learner. So, if you are new to the world of AI machine learning, PyTorch is great one to pick up. It's not that difficult to learn and it has low barrier of entry. And if you are learning perhaps a new machine learning algorithm, it might be good to first try it out in PyTorch before moving to something else. And similar to TensorFlow, PyTorch also has a very extensive community of developers and it has great documentation, which means that if you run into trouble with PyTorch, you are going to be able to get a lot of help. But what it does lack though is the visualization capability of TensorBoard. So there is no real visualization component to PyTorch, meaning that you don't get that instant feedback to see how well your algorithm is really performing. Another framework is called Caffe. Caffe stands for the convolutional architecture for fast feature embedding. Now, as the name implies, it is really focused around convolutional neural networks or CNNs. This is deep learning, so it's really geared around speed of image processing and image recognition, and it really does well at this. It's used by applications that need video analytics and computer vision all over the world. But if you need it for something else, it has very limited capabilities. So it's really focused on this particular strength. It doesn't have the same granularity within the neural networks like TensorFlow and PyTorch. So you can't really tweak the neural network the way you want. But if image processing is what you're after, then Caffe is really a good option. So essentially, it's not intended for non-computer vision or non-video analytics deep learning applications, and it's really focused around specifically video analytics. Finally, we have Apache Spark MLib. Now we know that Apache Spark is a great framework for streaming and batch analytics, but if you are using Apache Spark, you also inherit a very rich machine learning library called MLib, and this includes capabilities for classification and regression, clustering, dimensionality reduction like PCA, and many others. Now, why would you want to use MLib over something else like PyTorch or TensorFlow? Well, this framework also has a very easy entry point, and if you are having an Apache Spark framework already in place, then just adding MLib is like an add-on. So it really makes it very easy to just continue adding it without investing time and energy to learn a new platform. So it has a very easy to use API, and if you are using Python, it's very easy to code too. And it has all the scalability capabilities of Apache Spark. It has a distributed framework, and so if you are having a very large Apache Spark network with many different servers, you can definitely apply machine learning on that very big distributed system, whether it's big or small. Now, one of the key advantages again, if you have Spark in place, it's just an add-on and it's very easy and compatible framework to what you already have in place. So far we've talked about the algorithms and the methods of machine learning and AI, things like classification, regression, deep neural networks, but what we haven't talked about is how do you actually implement this on hardware. Now when you think about unsupervised learning, it involves massive amounts of data. Perhaps this is a scatter plot. It could be a million data points. If you were to apply the k-means algorithm and you need to start to calculate the centroid and the cluster boundaries of that data set, it can be very computationally expensive. There could be millions of calculation that is done by hardware, and it could be done very slowly because each calculation has to be done one at a time in serial. These are computationally expensive algorithms, and the same thing can be said for regression and many other types of algorithms. For example, neural networks involve a significant amount of parallel processing. You have your vertical hidden layers and then you have horizontal layers in different neurons. Now, this is a parallel construct. If you were to try to get a CPU to do this in serial, it will be very slow and will take a lot of time to execute the entire deep neural network. A CPU is like a general processor. It's good at many different things, but it's not really specialized at any one thing. Now CPUs have been the mainstay of computers for decades. Everybody uses them. We are very familiar with them and we like that because they are so flexible. We can use them for almost any task. Now the downside of a CPU is that if you have to do a very specialized task that requires hardware acceleration, it might not be able to do it as fast as a different type of processor that was specifically designed for that task. Also, CPUs are very serial in nature. They process things in a linear fashion even if you have multiple cores on the CPU, and you will be limited by that few number of cores that you have. We can think of CPUs as kind of a Swiss Army knife. A Swiss Army knife is great because it's a tool for almost everything. You can have scissors in there, you can have a nail filer, you can have a magnifying glass, almost anything can be in a Swiss Army knife. But if you had a surgeon that was going to do an operation on you, How would you feel if he pulled out his Swiss Army knife to start cutting you open and do his surgery? I think we'd all pretty much freak out that he is using the wrong tool for a very specialized job. On the other hand, there's a specialized type of processor called GPU, or a graphical processing unit. This is a very specialized processor which is good at certain tasks. So, if your surgeon came in with his toolkit of a very useful tools for that job, you would have more confidence that he probably can do the surgery very well on us. Well, that's what GPUs are to machine learning. They are a very specialized processor for a very specific task. Graphical processing units, or GPUs, were first introduced by Nvidia back in 1999. They were really introduced in the gaming industry to accelerate graphics. So, if you are a video gamer, you wanna go out there and buy a really good GPU and show off to all your friends on how well you can do on your video games. Now they are really designed to process data in parallel, which welds itself very well to the video graphics world because there are so many operations that can be done in parallel. It manipulates and alters memory and accelerates images for graphics very fast. And it's good at something called as texture mapping. If you think of graphics, we have pixels. Every pixel has a color, has a shade. This is the texture of the pixel. And GPUs are very good at managing and altering the texture of those pixels. Now, while it was very well used in the video game industry and other types of graphic applications, around 2005, when deep learning started to become popular, a new use was found for GPUs, and they worked really well with machine learning and especially with deep learning neural networks. For example, here's a modern server that uses GPU. This is a server that has 8 Tesla V100s. These are Nvidia GPUs. Each GPU has 640 tensor cores on it, and that's over 5000 cores on the server. So this server is very specifically built to do a machine learning workload. You would never buy a server like this and just do general processing on it. This is one that's specifically designed and built for big machine learning and AI projects. Again, to compare GPUs and CPUs, GPUs are all about parallel processing, and it can do this because it has a lot of cores. Not just a couple of cores like a CPU, but it can have hundreds if not thousands of cores that can each handle a different aspect of machine learning job, and it can process them all in parallel at the same time. Parallel processing is what makes them so useful in the world of AI and machine learning, and especially this is true when you have a lot of data and when you have deep learning. Now the number of parallel computations of course depends on the number of cores. So if I had a very large deep learning neural network, I can put all of these onto different cores on my GPU, and it's going to process them all at the same time. All the different neurons will map essentially to a different GPU core. Now imagine if I was to do this on a CPU. The CPU is probably going to handle this one step at a time. So if I had 1000 tasks that I needed to be done, they could literally happen at the same time on the GPU, whereas on the CPU it would take 1000 times longer. Think of a job like k-means, for example, where I have to calculate the distance from each data point to a hypothetical centroid. Making that distance calculation and then trying to find the cluster boundary in a CPU would take a long time because every data point needs to be calculated individually. But in a GPU, I could do literally thousands of computations at the same moment. Now, when is a GPU perhaps not as ideal as a CPU? Well, there are cases of serial processing. So let's say there is a job that doesn't really need a parallel abstraction. I can't break it down to a bunch of small different tasks and do them at the same time. In that case, the GPU really isn't doing much for me because there is no parallel computation to take advantage of. You may have to process it in serial just like a CPU, and a CPU is generally much better at doing that. So GPUs do very well when you have a complex task that can be broken down to a lot of very simple ones. There is a technical term for this, and it's called embarrassingly parallel. It sounds like a funny expression, but this is when a complex task can really be boiled down and split into a lot of smaller tasks that you can do in parallel. So we often refer to GPUs as following an embarrassingly parallel architecture. So for example, going back to k-means, does it take much effort to measure the distance between a data point and its hypothetical centroid? Well, no, that's a very easy, almost embarrassingly easy calculation. I can do a whole bunch of them at the same time in parallel. So that could be an excellent example of an embarrassingly parallel system, whereas on the other hand, a CPU would do it one at a time, being very inefficient because it doesn't follow that architecture. Another example of where an embarrassingly parallel system is useful is in digital graphics. And of course, video analytics and deep learning are a big part of this. In digital imagery, GPUs help to put pixels on a screen, but how do you decide which pixel goes where and at which color? You can think of three-dimensional images really as just a set of coordinates, and each pixel has a color, which of course we call the texture. This involves a lot of three-dimensional geometry. Everything on the screen needs to be calculated. Think, for example, if this is a first-person shooter game and the bullet is flying out of a gun. How do you know where to draw the bullet as it passes across the screen? That's all geometry. And it's a lot of matrix algebra and linear algebra involved. This involves a ton of 3D calculations, and that's what GPUs are very good at. In graphics, we pull out what can be done in parallel and make sure that those jobs are processed at the same time. Now, as it turns out, many of these equations involved are being done in parallel because they just don't depend on each other. For example, in this picture, what we see is a lion, but what the computer sees is a whole bunch of pixels with a different color. Those pixels come from calculations produced by a GPU. And think of the example of neural networks. This is an excellent example of an embarrassingly parallel system. Neural networks are very useful in the world of video analytics, where you take in a raw image, you break it down to its basic features, and you have its mid-level features and your high-level features. And these are mapped again to hidden layers within the neural network. Inside each hidden layer, manipulators, you have the neurons. These again are mapped to very specific tasks in a GPU core. Each one can be handled independently and in parallel, making the GPU a very key contributor to the world of convolutional neural networks. In fact, we can say without GPUs, we would really not be able to do deep learning effectively today. So, if we take a look at what happens inside a deep neural network, you have an inherently parallel architecture, you have some complex matrix operations, and you require a lot of bandwidth, while GPUs can serve all of those requirements. So, if I have a GPU, how exactly do I program it once I build my model in things like TensorFlow or PyTorch? Well, CUDA is a wonderful way to do this. CUDA was developed by NVIDIA as an API for developers to actually program into the GPUs to make sure the cores are assigned to a very specific task, for example, in a deep learning model. We can think of GPUs as the hardware, whereas CUDA is the software that architects and programs that GPU. Now, CUDA includes GPU acceleration libraries through cuDNN or CUDA Deep Neural Networks. And if I'm using things like TensorFlow, PyTorch, Caffe, whatever, it has a direct compatibility with the CUDA API, allowing me to program the GPU. For example, with PyTorch, CUDA comes baked in with no additional downloads required. So, if you already used PyTorch, you don't have to interface with the CUDA API directly. You have a direct connection to the GPU through that linkage. We now have a good handle on GPUs and how they are used to accelerate machine learning jobs like deep neural networks. But there's also a shift in the industry where GPUs are being used in a more general sense. This is called General Processing GPU or GPGU or GPGPU. Now we can think of the CPU as the jack of all trades, Swiss Army knife that can almost do anything. While there is a push to make GPUs do similar things, now although it's not really well designed for that, with CUDA we do see the possibility of using that GPU in a more general sense. So we'll see over time as GPUs become more general purpose, and perhaps over time they will even begin to compete directly with CPUs for general tasks. Now, as you might be knowing, Hadoop is great for distributed compute and allows you to bring processing jobs to where the data is rather than moving all the data back to one central point for analysis. It's like getting all your minions to do the work for you and then just returning the result which you combine. That's what makes Hadoop very powerful in massive datasets. Now, in the cases of GPUs, they can also play a key role here. So let's say we program the machine learning job with PyTorch, TensorFlow or MXNet or one of the other popular machine learning frameworks. Now we are gonna run this on our Hadoop framework. But we want to accelerate the job so that our data nodes in this case become more specialized. We are going to have a GPU powered data node and perhaps we are going to use the NVIDIA CUDA cores where we run our YARN containers. This will allow us to run things like PyTorch, TensorFlow directly in that container, program the GPUs to accelerate and process our jobs in parallel. Now, as much as we have seen GPUs take center stage in the world of machine learning, there is a new class of hardware that's starting to emerge, and this is very specialized hardware just for the job of machine learning. So GPUs are great because they can do things in parallel, but really they are being borrowed from the world of graphics acceleration. When we look at very specialized hardware, this is the hardware that is built from the ground up to do machine learning jobs. One example is the TensorFlow processing unit built by Google or the TPU. TPUs or TensorFlow processing units use a CISC architecture, that is complex instruction set computing design. This is contrasted with the RISC, that is the reduced instruction set that you see on many CPUs. Now, why do we have a complex instruction set? Well, what it allows us to do is put rich machine learning libraries directly onto the chip itself. In other words, TPUs are built and designed to do machine learning at wire speed. For example, machine learning often requires very complex linear algebra computations such as matrix manipulation, matrix inversion and transposition. These are processor intensive tasks, but with Google's TPUs and other similar types of hardware, it's able to perform hundreds of thousands of matrix operations in a single clock cycle, and that's pretty impressive.